Very good afternoon to all distinguished speakers, professors, researchers, students, participants. And I'm Dr. Debashis Panda, convener of the program. Heartily welcome you all in the today's talk in the international webinar series on novel materials and devices for supercomputing 2020, organized by Department of Physics, National Institute of Science and Technology, Berhampur. As some of you are not joined past stage, for that I like to remind you once again, a feedback link will be provided in between the talk in chat box. All are requested to write your queries about the talk in chat box to me only. I request you all, please stop your video and mute your audio. Just I like to tell 2-3 lines about our institute. The National Institute of Science and Technology was established in the year 1996 by a group of academicians and technocrats educated in the top institution of India and abroad under SM Charitable Educational Trust, where Professor Sangram Mudali is the former founder secretary and administrative head since inception. This is the first NRI educational venture in the state of Odisha and southern Odisha. Keeping true to its core value, mission and vision, NIST has become a top-notch institution in the state and country since establishment. Now I'm requesting Professor Salila Das of Berhampur University to introduce our today's distinguished speaker, Dr. Santanu Jana. Madam, please.
Okay. Hello, everyone. Welcome to today's webinar. It is a great pleasure to introduce today's speaker, Dr. Santanu Jana from Portugal, who is going to talk us about colloidal quantum dot. Colloidal quantum dot offer a striking visual demonstration of quantum mechanics. Today, Dr. Jana is going to share a very interesting and challenging topic, so I think everybody will enjoy it. Coming to his achievement, Dr. Jana did his bachelor's and master's degree from the University of Calcutta, a premier university in India. He holds his PhD degree from the same university and has 4 years prior experience working on Indian Association for Cultivation of Science, Calcutta, India, in Paris, in France, and served 1 year in Singapore Bioimaging Consortium Agency for Science and Technology and Research. At present, Dr. Jana working as a research scientist in Sinamit University in Nova de Lisbon, Portugal. He has received several awards, fellows like prestigious Marie Scoldia's Curie Individual Fellowship in 2015 for postdoctoral research, Sienna's postdoctoral research at Brussels, Best Poster Award from Optical Material International Conference of Young Researcher in Advanced Material Singapore, Young Scientist Award India, and many more. Dr. Jana has a number of publications in high-impact journals like Nature, Electronics, and so on. With this brief introduction, I, Dr. Salila Das from Berhampur University, on behalf of NIST, like to request Dr. S. Jana to deliver his talk on colloidal quantum dot, a building block of nanoscience and technology. I transfer the screen to Dr. Jana. Next, we would love to hear from you, sir. Please.
Thank you so much for kind introductions. And first of all, this is my first webinar. Anyway, I gave some talk on online, but this is my first webinar kind of things. And first of all, I like to thank all audience and all professors and who are listening. And I should say that my background is completely chemistry, but I changed my field like inorganic organic chemistry I did, but I changed my field during my PhD. It based on quantum dots and their applications. Though in PhD I did not do any application, but in here I joined as a assistant research scientist, and I started to do my application like a kind of TFT, thin film transistors, and like memory devices and other things. But as I am not so much expertise on electronics and other things, and my main topic is mainly on the quantum dots, mainly chemistry part. But I like to take it very easy I will not talk about more on chemistry. I like to talk about what is quantum dots and how it behaves. Maybe many people knows that, but I like to introduce more details in the quantum dots, how it behaves, how it works, and how is the fluorescence works, how is the applications and other things. So this is my basic thing. So, and I will also tell about some of my work because as I told that my work is mainly based on chemistry, so I do not want to go details on that, so people will get bored. So I do not want to make people bored because it is an online version, so we do not see our face, so that's why sometimes people are getting bored. So I like to, my topic is that like you can see the colloidal quantum dots, a building block of nanoscience and technology. Okay, first nanoscience and technology. Okay, people make the nanoscience and technology like a there is so many things like a silicon technology, and now people are come to the nanoscience, and because when you goes to the nano regime, you will have a more space to do the things. Like if you make some electronic device, you have more space to put so many things in together. So because you need only the small material, but their activity is much more than the bulk. So but why quantum dots? First we need to know the what is quantum dots and how it behaves, and why we tell it the colloidal. So first I should say the what is quantum dots. It's a it's not changing. Okay, yeah, it's a very small crystal. Small crystal means like 1 to 10 nanometers, and it has a very unusual property. And you can see, okay, in nanocrystals, you can see the nanocrystals 1 to some people say 500 nanometer, and it's scaled, it's shaped the nanomaterials. But I think it's not nanomaterials, because you can 1000 nanometer you can say, but nano, when it goes to nano, it should be the 1 to 100 nanometers regime. And when it goes to quantum dots, quantum regime, quantum means it should be the confined along the band gap. So that means it goes to below the diameter or length or radius, whatever you see, sometimes quantum rods, quantum platelet, it should be below their effective radius. Like a cadmium selenides, it should be below 6 or 7 nanometers. So 1 to 10 nanometer, generally 1 to 10 nanometer is a perfect for the quantum dots. So why we say the quantum dots? As I said, it's very tiny crystals. Then what is the behavior of the quantum dots? Sometimes people say it's an artificial atom. You see, first, I see quantum dots are very small particle of semiconductor. It should be semiconductor. Otherwise, the like a electron and hole cannot be confined along the band gap. And typical dimension is the 1 to 10 nanometer. And like a just an atom, like we know that the atom has an energy level is quantized, means very discrete, and where the electrons are confinement. Similarly, quantum dot is a very maybe like if you have a 2 nanometer or 3 nanometer crystals, it has a maybe 20 or 30 or maybe 50, 60 nanometer, 60 number of atoms together. So depends on which quantum dot you are using. So depends on that. So that means your electron and hole are still confined along the valence band and conduction band, and like so it has many things, many properties like atom, like a broad absorbance, narrow emission is narrow emission, like in atom we can see the narrow emission. Similarly, quantum dot has a narrow emissions, and also the wavelength dependent on size. Why wavelength on dependent on size? That I'll talk about in the next slide. You see, that's why sometimes these quantum dots called as artificial atom. And you can see the nanometer scale, its atom is close to 1 angstrom. Then it's a dye, it's close to 1 nanometer, and quantum dots behaves between the 10 nanometer region. And then the colloidal gold, it's close to 100 nanometer, depends on 50, 60, 100 nanometer. Then bacteria, it's 1 micron, and animal cell is close to 10 micron to 100 micrometer. So generally quantum dots, which all kind of quantum dots falls between the 2 nanometer to 10 or 15 nanometer. So why it has a dependent on wavelength, means dependent on size quantum dot. Like a is you people are background is physics, so you people know better than my I did it very small, but you people know very well that on the band calculations and theory of the band calculations. You can see the bulk 3D material. It's a bulk material. There is two band gap, valence band and conduction band. It's a semiconductor first of all. So, and there is the band are not quantized, means it has when it's the orbital are overlap, it's not quantized, so it's a continuous energy level. So when it goes to the 1D confinement, means the like a one-dimensional confinement means the electron are quantized along the one directions. So other two direction, and electron can move along the one direction, like you can see here where it is written is a quantum well. So quantum well generally people do, it's a basic one lower band gap material inside and two large band gap material outside. So it's quantized. So it's quantized between the lower band gap. Exciton means electron and hole quantized between the one along the plane. And when it's quantum rod, it's a 2D confinement, means electron can move along the one directions, and other two direction is completely blocked. Electron cannot move. So it's a 2D confinement. So that's why it's the energy diagram is like that, saw-like, and electron can move along the z direction, means one direction. Now it's a quantum dots. It can see the 3D confinement, means electron. It's a kind of particle in box, means everybody knows that particle in box rules. It depends on it depends on inversely proportional to the length, and the energy is inversely proportional to the length. It's similar, like it behaves like a particle in box. That's why you can see the when size increases, you can see it's a bulk semiconductor, like a bulk band gap, and you can see the band is like it's example of cadmium 2+ and selenium cadmium selenides. And generally the valence band forms with the hole which belongs to the selenides, and conduction band forms to the metal ion, like a cadmium 2+. So it's a molecular orbital, and there is so many band. So here when bulk band gap when this go to the nano regimes, when beyond their lower their and radius, effective radius, you can see the energy diagram is getting discrete. And so when this exciton separates, and when you can see the size increases, so band gap completely decreases, means it's similar like a particle in a box. So energy is inversely proportional to the length of the size. So that means when your particle size is high, so your particle size is big, it's going to be slowly bulk band gap, and you do not have the property or proper property of the quantum dots. But generally which material could be, you cannot make the whole material in a form of quantum dots, because we do not have a semiconductor in the periodic table. Mainly, like many people knows that mainly chalcogenides like cadmium sulfide selenides, zinc sulfide selenides, it's a good semiconductor material, except silicon. Forget about silicon. Silicon has a now minimum property, but we are try to change belongs to the quantum dots. And also there is some 3-5 material, group 3 material, and 5 like a group 5 phosphide and arsenides, but these are little bit more toxic, more hygroscopic, means if you take it in air it will collect the moisture very fast. So that why it is not still yet focused. But and also there is another lead and tin sulfide. Tin is not very good material, because tin generally oxidized tin 2+ and tin 4+, so it immediately changes their property. But people are mainly focused on the cadmium, zinc, and sulfide, selenide, telluride. So cadmium, selenide. Now, how we do the material preparation? There is lot of kind of material preparation. Like many people, the physics people do their like I just can go directly. Like they generally do the instrumental process, like a lithography, different etching process, like a deposition. That means we have a very simple way. I can see you have a big rock, and you can just cut one by one by like lithography. You can design your crystal how you look like, so you can do it like that. But we do in the chemical way, like you have a, like here in example, you have a small wood and you have a pin, so you can make it a big way. So similarly we have a precursor, different kind of like a different salt, and we have a different solvent, different solution, and we can make it in, it's called a bottom-up technique, and we can make it a very way in the quantum dots, mainly nanocrystals in different way. So now how we use and why it's famous for the quantum dots. Generally it looks like very tough for physics people, because when I set up here in CENIMET, because here the all people background from physics and electronics, when they saw, they tell that it's very complicated. But when I did it, and everything is normal, and it's a very simple way. Means it's not a complicated, because people, the physics people does not like so many solutions, so many wires are connecting, and so many things are controlled. They like to connect the instrument, but not in chemistry in solution. Like here you see, it's a just simple temperature, means your magnetic stirrer. You have some temperature controller here. You can give a temperature, and it's a 3-neck flask. You have a solution, and you can inject from the 3-neck, one neck you can inject the precursor, means for like a cadmium selenide, you can add cadmium, selenium, and other precursor, whatever you like. And it's a temperature sensor, so you can change your temperature in the solution. Generally we do in the high temperature in 200 degree to 50 degree, mainly above 200 degree, depends on which quantum dot you are making. So you can control the temperature sensor, so, and you can fix the temperature, and it's generally reacts on the under inert atmosphere. Mainly you use nitrogen, and you can use the argon also. Some material you need to use the argon, but otherwise nitrogen is fine. So you can pass the nitrogen inside the solution. So when it's complete, you can clean, and you can collect the dots, your rods, or your different size of particle and other things. So why we use, there is also other chemical process like solvothermal and other things, but as my experience, I can say this is the best way to make the homogeneous particle. Why I am telling, like in solvothermal, means you can put the all together inside a vessel, and you put it inside the heat chamber. So you cannot control your solution, you cannot control from solution. But here it's in high temperature, but you can control your solution. Like you can add the precursor, you can add the solvent, you can add whatever you like. Like you can, if you need to grow a rod, you can you need to protect the other two side of the nanocrystal, so it can grow one dimension. So that time you can add the solution and it can grow. So you can have a almost all particle in the same size or same length and whatever. So it can give the homogeneous particle. So I will show you some TM images, transmission electron microscopy images later, how it's beautiful. So how it works, like it forms a crystals, and some organic ligands, it's attached to the surface of the nanocrystals. It's when it forms the ligand like a different kind of amine, different kind of acid, means it should have a long carbon chain. So this carbon chain, due to this long carbon chain, it's dispersed in the non-polar solvent like a hexane, toluene, chloroform, and this kind. Of course, you can transfer to the polar solvent, but you need to then change again the ligand after formation of the nanocrystal, because generally we use the high boiling solvent like a non-polar solvent, because polar solvent like a water and other things like ethylene glycol, it reacts with the nanocrystal ion, and it destroys the growth of the nanocrystal. So that's why we use the non-polar solvent, and it works very well. And maybe this is one video how it reacts. Like it's a you can see it's a temperature controller. You can inject from here, and you can see it's growing the nanocrystal from here, and it's very fine. You can see it's glowing inside the solution, and we can here take out the solution in the vial, and you can collect in different time scales, so it can grow in different size. And you can see it looks like black, but it's not black. It's a very concentrated solution, that's why. But when it's grow, it is different, three different color, blue, green, and other. But if under the UV lamp, it's glow very well. Just end of the video, you can see it. So when you emit the light on that, yeah, you see the green, yellow, and okay, we did not grow it in the red. It's one of our past lab, so I just add the video. You can see it's red. You can grow up to more red, means around 700 and 800 nanometer. And you can see, as I told in earlier, you can have a very highly homogeneous nanoparticle and nanocrystal. You can see all the nanocrystal looks like same, means all at the almost 8 to 9 nanometer, 10 nanometer, something like that. So this is the best way to do the colloidal, and that's why we tell the colloidal nanocrystal, means colloidal quantum dots, because it's dispersed in the solvent and it's behave like a colloidal. And you can see the how it's crystalline. It's very highly crystalline, and you can see the atom, means very well. The white part is the void, and the black part is the atom, means it's a high resolution TM image. In scale bar is 5 nanometers, so you can see the atom very well. Means that's why in earlier I told that it's called the artificial atom, because you can see that the number of atomic, it's a little bit bigger nanocrystal, that's why, but the number of atoms, it's not so much. It's maybe 10,000 number of atom is there, and so that's like that. So when you change the particle size, you can distinguish the different size of particle. Oh, sorry, I can. You can see that it's the absorption in changes from the 400 to of course 700, means you can get the whole visible window absorbance from the nanocrystals, and you can collect and you can distinguish the different band of the from the absorbance. Like this absorbance, you can see this is this kind of transitions, 1s to 1s and other. So that's why I told you that it's in earlier, it's a quantum confinement along the bands and other things. And when you take it the emission, you can see the emission changes from the blue to red, just changing on the particle size, nothing else. I mean, you do not need to change anything, just you do the synthesis little bit longer and collect the sample in different time, and you can see the different size of particle, and you can see it's nicely distributed, the emission. So that reflects your nanocrystal size also. And you can see in the vial how it looks like. That is, band gap decreases, particle size increases, and you can get only simple nanocrystal, single nanocrystal, you can get from violet to the completely red. So no need to, this is the beauty of the quantum dots. I mean, you do not need to go to different addition of the ion, different addition of the other things. Only one nanocrystals, just size changes, you can have all the color during all the color in your visual spectrum. So there is many kind of nanocrystals in later people found, like a core cell. Generally in the core cell, like a core cell is the cadmium selenide and zinc sulfide cell. So it's called type 1, means the zinc sulfide is a large band gap, it's covered with the lower band gap, so it's stable emission. So like you can see the separate between the electron and hole, so it can not go to the outside of the solution sometimes when it's inside the solution solvent like a hexane toluene, so there is some moisture, so it can destroy your nanocrystal, it can create a trap. So if you coat with the zinc sulfide, so it cannot be trapped, so the emission will be more stable than the naked one. So it is the opposite way also you can do that. That is reverse type 1, but it is not mostly focused because it is not important. Mainly people, the lasing people, they do, because you can see the very thin cadmium selenide layer, so it is not very important, people not focused. But there is another one, type 2, means Type 2, it's called two band gap alignment in different way, like it's a cadmium selenides. Here is the band gap valence and conduction band, and zinc telluride, it's coated with the zinc telluride, and the band gap is different. So when you excite the light, so the recombination emission is coming through not the direct band gap, it's in other indirect band gap kind of thing. So emission, you can get the emission in different way. So your absorbance and emission is different. So that's why people use sometimes type 2 for the for mainly for like a bioimaging application. So there is no reabsorbance process and other things. So, and you can see that you can grow, as I told you, we can grow very nicely nanorods. You can see this is very nicely nanorods through the adding by ligand, different ligand, and all the rods, the length are very nice. And also the tetrapod, from the simple crystal you can grow the tetrapod, means one, there is, you can see only 3 leg, but other leg is behind the dots, so you cannot see the all 4 legs because it's only 2-dimensional view, it's not a 3D view. So once it's a 3D view, you can see the 4 leg, but you nicely grow the one side of the crystals. It forms it's grow from these kind of small tiny crystals, and you grow only one pod, and it's only it happens you using the different kind of ligands and other things. So it have a different property and it has other kind of things. So let me tell you like some of my other work, it is a previous quantum dot. So mainly I worked on the platelet make a quantum well systems, as I told very earlier. When it's go to the 2D one-dimensional confinement, it's called quantum wells. It's a cadmium selenide platelets, and you see very nicely it's kind of plate, it's a rectangular plate, and you can see this one direction is very confined, and it's only 1.5 nanometer thickness, and you can see only 5 atomic layer is there. This is cadmium, this is selenium, and you can see cadmium selenium, it's only 5 layer is there, and you can very highly distinguish the cadmium selenide. And that's why the exciton is confined along the one direction. That's why we said it's the colloidal quantum well, and you can distinguish by the different layer. We can synthesize from the 2 monolayer. You can see 2 monolayer means only 2 layer of cadmium and selenium layer. Many people this kind of things, this kind of very thin layer of things, people using the high configuration instrument, but we do it by the hand, in the solution phase, and there is no mixture of different kind of thickness. Like if we have a 3 monolayer or 4 monolayer, we will have only the 4 monolayer of the platelets. Like you can see from the absorbance, there is no mixture, and you can strictly distinguish the different layer of the platelets. This is 5 monolar, this is 4, this is 3, this is 2, and we can control the thickness 0.3 nanometer, means only half of a lattice parameter, means 1 cadmium and 1 selenium atom. We can grow by the atomic layer by solution process. It's very interesting. And synthesis and purification is homogeneous solutions. As I told that there is no mixture of the platelets. You can have only the simple 4 or 5 monolayer, 3 monolayer platelet, and it has a outstanding optical property, means the absorbance coefficient is super high, almost 10 or 15 times higher than the normal quantum dots. And so as it behaves as a quantum well, and it behaves like a latching and very short lifetime. It's not very old material. Quantum dots the synthesis started from the 1993. So, and it's almost 30-year old, but these platelets are almost 6-7 years old. So people are still investigating on that, how it behaves, how self-assembly and other things. And how we synthesize, we generally synthesize, you see, 2 different kind of precursor, and it's grow small platelet, and then you can grow the one direction. The solution looks like this. You can see it's very transparent. There is only light color, but it's very bright. If we under the UV light, you can see it's strong green, and emission, and this is the absorbance and emission spectrum. And you can see the emission is very sharp, like atomic like kind of emissions. And the emission wavelength thickness is close to thermal temperature. So in the room temperature, you can see the very bright emission. You can see we can synthesize also. It's now people are trying to do with this kind of material because it is very stable and there is no broadness of the emission, so we can use in further other lasing purpose and other diode process, other like LED and other things. So it's called now few people are telling that it's the next generation of quantum dots. And you can see this is embedded in the PMMA, and it's very beautiful. It looks like very beautiful. We just took this image for the presentation, for the presentation purpose. It's not kind of research, but this is the things. And you see it's a platelet. It's a 4 monolayer platelet, and you can see these are square, and very nicely all square is almost same. And this is a 5 monolayer platelet. It's a rectangle, and of course you can change the rectangle to the square, depends on your precursion and other things. So it does not matter, it does not change a lot your property, only the thickness of the platelet changes your property. So I did generally the self assembly of the platelet, and we just use some solvent of the solution, disperse, and how beautiful you see. These are like a rod or thread, you can say, but it's not a it's not a one crystal. It's attached with all platelets together. If you go to zoom high magnification image, you can see these are platelets stacked along the direction, and you can see these are the along the direction. And interesting thing is that when it goes to this kind of things, your nanocrystal has a fast station. Means they do not like to stand all together in the same fashion, so they have a super fast station when they attached in the along the one directions, and the attach it all are goes through the solution. So they try to rotate, and they try to release their space and release their energy, and they try to stabilize them. So that's why you can see the rotation along the direction, and this is beautiful things to get the how it's rotate inside the nanocrystals. And generally we know the crystal cannot be bent, means crystal is a very strong material, means strong, it's a, but first time we have observed that crystal can be bent. So we do not have the theoretical support and other things. We just experimentally we saw. You see that crystal, that part, it's bending, means only one crystal, one part is bent and another piece is not. You see that it's a 3D image. I can show you the video, so you can see the how beautiful it rotates and other things. So you can see the gap between two platelets are completely same, and there is some meshing. Maybe this is due to some evaporation and other things in the TM grid, but all the platelets are same, and it's two state in the along one direction. So it's only due to the frustration inside the nanoplatelet chain. So these are my last postdoctoral work. I do not like to go more details on that because it's very more specific and more chemistry purpose, so I do not want to tell you. But this is one of the most new material and which are exploring, and also there is no electronic application, so I recently started to do on this application on the TFT and other things on this material. But I like to introduce some of the my past work. It is very interesting and very easy way to understand. It's called doping in semiconductor. As you know, doping in silicon, you can dope the p-type, n-type, and other things, so you can change the property of the silicon. But our aim is the change of the, here also we change the property, but we change the emissions of the doping. Like here is a crystal quantum dots, and you have a different selective transition metal ion like manganese, copper, and other material also you can use, and it goes there, and it does not put in void space like n-type or p-type dope in silicon. It just replace one of the, it's a ion exchange, it's replace one of the atom of the crystals, and it removes. And when it goes the inside of the crystal, and then you can grow inside the solution like copper. If you put the copper ion inside the crystals, it creates some energy level inside the band gap, and when you excite the UV lamp, you will see the you could not see the mother emissions. You see the different emissions from the same crystals, like because of it has create some energy level diagram in energy level in between the valence and conduction band, and it emits through these three directions. So it's completely unexpected why the emission is like that. It depends on many property of the transition metal ions. And also manganese, it has a two different band diagram. So exciton transfer to the manganese part, and you will emit you will see the emissions between the orange emission from that. I will show you some image of the nanocrystal, like zinc selenites. You will see under UV in the dark it's blue. When you put the manganese, you will see the very bright orange emissions, and then copper, it's very bright green emissions. And if you put the manganese and sulfur, so because it shifts to the red, so it's dark orange, it's yellow and it's dark orange emission. And doping is very less, the 1% or like something like that. And yeah, of course, another one interesting things that after changing the band gap and other things and putting the doping, you also change the from whole visible window emissions like a blue to red. It's not explored very well. We just did the synthesis and other things, but we need to explore more other way, other application purpose, like it's very bright and other things. It can replace the only the quantum dots. So you can see that only one port synthesis, you can start from the blue emissions, and you put to manganese, just putting the different ion, you will have the different color of the emission in the only one pot. You can see the in the pot, previously it is only the zinc selenites. You put manganese, you will have a blue yellow emissions. Then you put copper, again you will have the green emissions, and again you put cadmium, you will have the red emissions. So interesting, just only one pot, you can change any emission, any different emission, just adding the different kind of cation inside the solution. You do not need to change anything else, and the particle size will not change and other things. So this is the material purpose. This is the doping. So interesting of doping. So you can have a different kind of emission by just adding the different foreign ion. And it's nothing, just the mechanism is nothing, just when you add the cations and anions, so it creates different kind of energy diagram, different kind of defect energy in between the valence and conduction band. So that's why it changes the emission of the light. And other things, you can change to this kind of material in the water for the purpose of the biological emissions. And you can see the another atom, another nickel 2 plus, so you can have a magnetic property from the doped nanocrystals. And also you can see it's very highly stable in water, it's boiling water, you can see vapor, and it's different pH, so you can use for the biological emission. Already there is some application from our past lab, they did some cell imaging and other things, and also other nanocrystal doping in other nanocrystals. These are my past work. And so so now what people did, some application purpose. You see the quantum dot LED is a more it's a very high brightness is very high, so you can use the LED, and already people use the LED, and many and also the display purpose like a quantum dot TV. I think in India also some bought big supermarket, we can see the quantum dot TV because it's more brighter than the other like organic OLED, and more stable because it's nanocrystal, and its longevity is more higher than this. And very recently from MIT they make some quantum dot spectrophotometer. So generally you use the very big spectrophotometer, but when it goes to quantum dots, they made already, and they file a patent. So it could be the one kind of smartphone. So through the smartphone kind of size, so you can use this kind of small devices for the measuring your absorbance and emission and other things. So that's why the beauty of the nanotechnology. So when you have a nanotechnology, so it can create the small, you no need to get a big instrument. So, and also nowadays people make another kind of so you can save the energy, you can say the light harvesting. So and another interesting part, people make the quantum dots for the solar cell. It's a NREL chart. It's a little bit old, but here you can go to the NREL websites and you can download the recent chart of the solar cell. Now people making the perovskites for the solar cell. I also started work on the perovskites, but I go to perovskite quantum dots, not the bulk perovskite for the solar cell. So these are the part where the quantum dots, perovskites, and lead sulfide quantum dots for the solar cell. And for the lead sulfide, I think it's now up to 16 or 17%, but it's beyond the imagine. Means it's still lower than the perovskite. So we need to more focus on the other technology to improve the solar cell. So I just go first in the perovskite part. It's another kind of semiconductor. Everybody knows that physics people. It's a calcium titanate structure like ABX3, and it's a perovskite material, perovskite structure. But we are most interesting in the not oxide perovskite. It's a halide perovskite, like a cesium lead bromide, cesium formaminium, or the methyl ammonium lead iodide, or this kind of organic inorganic. Like here you can see it's a colloidal synthesis. Again, colloidal nanocrystals. People make the perovskites for the bulk for the solar cell, but we generally work for the quantum dots. You can see this is solution in the quantum dots. You can make some. It's just funny things we made from the PMMA, and these are the nanocrystals which are very stable and homogeneous nanocrystal on the perovskites. And this is just how perovskite synthesized. It's a one kind of synthesis. You can see the very fast synthesis. This is not very good, but it's not very homogeneous, but it's very bright. That's because the absorbance and other things are very strong rather than the colloidal quantum, like chalcogenate quantum dots. And you can see here also you can get very bright emission from the full visible window. It's again perovskite quantum dots, and we have started working on the solar cell on the perovskite quantum dot like that. We use the perovskite absorber material in between the common things like N-type material, P-type material, whole transport layer. Generally N-type material we use the titanium oxides and other things, but we use the perovskite quantum dots to see how the solar cell works. So this is basically solar cell works, how we use the transparent conducting oxide and electrode as a gold. So you shine the light in perovskites, the exciton generates, so hole can go, electron can go to the transparent conducting oxide side, hole can go, so you have a circuit. And this is our small contribution to the solar cell group, solar cell part. It's not very high efficient, but we wanted to see how the perovskite exciton generates in between that by through the KTFM. Looks like this. So and recently we got it's 11%, but recently we got around 20% efficiency. And also we started with it's another kind of perovskite quantum dots. So that behaves like a solar cell. And also we like to use these quantum dots for the memory and TFT purpose. And like you can see this very bright emission, you can use the LED, and it's real device fabrications for the perovskite quantum dots. And you can see how bright is this. And now I like to, this is my whole part. As I told, I mainly focus on chemistry, but I try to not to focus on chemistry. So that's why I just try to brief what is quantum dots and how is the future and other things. Why still there is more room, more space to do the research on quantum dots, and it's like 20 or 30-year-old, but another 20-30 year it is easily can go before. Then after that maybe we need to think about another new kind of material like that. So as Dr. Panda told me to tell about some opportunity of the PhD and other things, as I spent a lot of the time in mainly France and now Portugal and also the Singapore very small times. I think in Singapore we need to get some GATE exam and get that score, and there is some process in every year, so we need to apply from there. There is no need to give any exam on that, but only some interview and other things. But for France, you no need to give any exam and any other things. You just direct apply to the direct professor who have some positions. You can see the CNRS doctoral scholarships. You can go to their websites and you can find any position is there or not, or otherwise you can check some of the big university there, like what I wrote, ESPCI, University Paris. I spent the Paris University 4 years, almost 3.5 years, and it's specifically more on only science university in Paris. There is no other subject, only physics, chemistry, biology, this kind of subject. And University of Strasbourg, CEA, Saclay, I just put it some big university. There is also other, but you can find it, their websites, and you can check it, they have availability or not. So you can directly mail to the professor and who has the vacancy. So if they choose, they can choose directly. You no need to give any exam and any other things. Just your CV, your experience. If generally they don't take outside other experiments. Suppose you have some spectroscopy related PhD vacancy. That professor was work on spectroscopy, so they like to take the spectroscopy or lasing kind of experience. So they do not go to, because the time spent is very small. They take only 3 year time for the PhD. Within 3 years we have to defense and everything, so they don't take beyond, because they have a funding problem, so they don't give beyond 3 years. It's a good for the PhD scholar because they can get the degree very fast. But sometimes I think 3 years is, in my point of view, 3 years is very small time to explore all the things. It depends on who is the scholar. Some scholar is very much smart, they understand everything, but not all other. I have seen some of the, they knows very well the topic within 3 years, but some they couldn't understand what is going on inside there. So sometimes it takes times, but it depends on people to people, but it's good to the research lab are good and other things. In Portugal, they generally don't take the direct things, and there is some fellowship every year opens, like you can see the PhD research scholarship 2020. This year they opened. I think it's closed or not. Again next year it will open. There is any other also MIT Portugal doctoral program scholarship. Here they take 3.5 to 4 years, but things are very good. The salary is also good, not bad. In related to Portugal, it's lower than the other European country, but the cost of the living cost is very cheap than the other European country. But here working culture is very good, and your lab facility is good. You can apply through this way, but you need to choose a supervisor of that. You need to write some proposal or some CV application of CV, but your facility and other things, and you are very good. You can, if you want anything about related to the PhD and for PhD and other things, you can write to me, so I can help. I can help if there is anything to know. So that's all. And at the end, thank you to all of you. So stay happy and stay safe, because we have a pandemic situation. So thank you a lot.
Thank you, Dr. Jana, for your nice talk. Very, very beautiful talk. There are some questions are there. Okay. Just I like to tell one by one. One question is that why the platelets are called quantum well? The basic question, I think.
Okay, it's a very basic question.
Yeah.
So it's a very simple thing. So you can show quantum well. You can show why people. You see that it's a quantum well. You can see the exciton means electron and hole is confined along the one direction. Basic quantum well, basic quantum structure. So when it goes to platelet, I can show, yes, when the exciton it's confined along this direction, mean z direction, mean electron hole, and this other two direction it's beyond the band gap, it's very big. So that's why when excitons along the one directions, it behaves like a quantum well system. It's that's why it's called the quantum well. Am I clear? I think it's same like a quantum well, means basic quantum well. It's electron and hole confined along the one direction, means z direction. You can see it's a very strong confinement in the 5, or this thickness is only 1.5 nanometer, means 5 monolayer, and exciton cannot move along this direction. Exciton move all the other two direction, x and y direction. So that's why it's called the quantum well. And if you see the emission, it's very sharp emissions, like same like a quantum well system, very thin, and the fluid half maxima is very small, very less atomic kind of emission. So that's why it's called the quantum well.
There's another question. Why is doping difficult in nanoplatelets?
Okay, nanoplatelets, first of all, yeah, we started to dope, but doping difficult in nanoplatelets because the synthesis procedure is a little bit different, not like a pure quantum dots. And yeah, here you can see it's a platelet, it's growth, when it's grow along the one directions, and it's a cubic, I mean the shape size is cubic, basic size is cubic. So like you can dope the copper it cannot go inside the platelet. When it goes inside, it getting frustrated, so it stopped growing in the platelet, then it started growing in the quantum dots. So that's why still we are trying to do the doping in platelet in the other way, not the common process.
So I
That's
think
why
it
it's
will.
a little bit.
I think it will be in the surface. It will be placed in the surface. I think.
Exactly, it will be surface, so that's why you will not get proper emission and other things. So this is the problem of the doping. So it can destroy your platelet if it goes inside, because it's very thin, so it can destroy. That's why it's very hard to dope.
There is some other questions are there. Just a minute. How the UVB spectra affect the particle size of quantum dots?
Yeah, you can see you can see the from the UV visible spectra, different size of you see the I dotted the angstrom, means it's 1.7 nanometer, 2 nanometer, 2.9 nanometer, and it's a 15 nanometer, means it's almost bulk. But when your particle size is different, here you can see the distinguish of the band very nicely. If your size is different, like we have a mixture of particle, we cannot see this kind of difference. Your absorbance is very broad. Maybe I do not have this kind of broad absorbance. Like here you can see the 8 nanometer particle, the absorbance is distinct, is not very well, it's broad absorbance. So that affects your absorbance. So when your particle is bad, not very good. So this is the initial way to distinguish your particle. It's after synthesis, it's a good or it's not, it's a good or bad, that you can distinguish very well from the absorbance.
Okay, so there are some questions about the higher studies. I think you influenced a lot for the students. So being a postgraduate in physics, how can I do a research in this field?
Yeah, why not? Everybody, I am chemistry, but I am now doing the electronics. So it depends on you how you absorb the field. Like like just for my example, when I went to the Singapore, it's a field of biology. Then I found that I cannot do the biology. Means after 1 year, after 10 months, I think that it's a very big field. Initially I don't like so much in physics. I like the physics, but no hardcore. Then thought, okay, I can do the bioemission, but okay, biological imaging, that is nothing in biology. It's you can image something else, then you can publish. This is nothing. I saw the hardcore biology, and then I understand it's not my forte. I cannot do the biology. It's a big vast field, but I can do the physics because I did some in masters, in graduation, some of the part in physics I know, I can understand. So if I then I shifted to the little bit like electronics, like TFT. I did not tell about the details data because it's my recent and it's still under processing. But I started. So you can do the quantum dots. You say just one example. My postdoctoral boss in France, he is hardcore physicist. Especially he more focused on theory, but he know very well in quantum dots. And because in France they do not have the lot of students, they do themselves the research, and he know how to synthesis, and he knows. So it depends on you. If you want to know, if you want to do, you can do. It's nothing. It's not very hard. It's not very tough. So just you need to choose your proper professor, proper lab to do these kind of things. Like you do not go to the proper synthesis lab. You need to go some who do the synthesis, who do the lump sum physics things. Like if you want to do some application like electronics, if you do some lasing, so you choose this kind of professor. So then you can learn also synthesis. You can do the physics part of things. So it's not a very hardcore research, hardcore chemistry. Okay, people do the hardcore chemistry that you don't need to do. You just need to do synthesize your material. So that it does not need hardcore chemistry. So it's very not tough. You can choose. You need to choose the right professor to do the research. So quantum dots and others. So now people are focused on perovskite. Perovskite is more easy to the cadmium chalcogenides. So it's very easy. So this is my suggestion. So if you want to do, you can do. There is no burden.
There is something some bachelor students some ask you some question. Can you please share some information regarding the master's opportunity for students? Like someone having prior experience in the research field is necessary, or related field of material science or chemical engineering is necessary.
Yeah, you can apply for the masters in France. I do not know about the Portugal, but in France,
Portugal is also the FCT funding is there.
FCT funding is there, but in France also you can nowadays 2 years ago they make a rule 30% student they need to take from the abroad. So 70% from their own country and 30% abroad. So you can apply there every year. They have some opportunity in like École Polytechnique. It's named Polytechnique, but it's one of the best engineering student in France. I mean, all over the world you can say. Means to get in there, it's very tough. If you have a degree from there, you will get a position all over the world. Means don't take about easy that it's named Polytechnic. Means in India Polytechnic means it's a lower grade. Here Polytechnic is so École Polytechnique, one of the oldest engineering lab in France. I think it's in Europe also. So there is a master's fellowship is going on, so you can apply from there. So you have an interview and then you can start. It's I think 2 years and then you can have a PhD and other things. So it's not very tough. It's
there is another question related to your work. I think when decorating one-dimensional material with zero-dimensional material, will the surface area of the material vary? In such a case, what will be its effect on optical property of the material?
Yeah, of course. When the surface, because it's like a rod and platelet. Just simple example. You can see the here optical property. You can see the emissions of the quantum dots means zero-dimensional material and absorbance. And when you go to the platelet, like here you see the emission absorbance is very different kind of absorbance. And when you go to emission, you can see very sharp. So that affects means that your fluid half maxima of the emission it changes because your exciton is not moving all the direction. It's confined along some direction, but in zero dimensional it's confined all the direction. So all the property changes. It's just one example here. It's a platelet. The absorbance and emission is, you can see it's very sharp, but when it goes to the three-dimensional emission is very broad rather than the rod, rather than the platelets. So that is just initial distinguished. You can check it's a rod or platelets or your quantum dots. So this is the things. It's very because your electron and hole is not confined along the direction. It can move other directions. So your emission and absorbance changes. This is the thing.
I think there are no more questions. Just I like
Okay.
to once again remind you, there is a feedback link already provided here. So
Okay.
please all of you give your feedback. And I'd like to thank you, Dr. Jana, for brush up our knowledge in the basics of the nanotechnology and clearing so many things to participants, such as definition of the nano, means people are nowadays are every day 500 nanometer, they are saying
Yeah.
nano. So
Yes.
these things,
Yes.
yeah,
You cannot say
yes,
the 500 nanometer is nano. Means
yeah,
you can say you can say in centimeter scale. Then you can put the kilometer. Then you can say point dash kilometer. You cannot say similar
exactly.
kind of thing. So
Yes. So, such definition of nano, quantum dot, confinement basics, and also very interesting results on the cadmium selenide quantum dots, etc.
yeah.
I think transition from semiconductor by metal nanoparticle doping, that is also very interesting, and application of
Yeah. Yes.
quantum
Yes.
light emitting diode, etc.
Light. Yes. Yes. That's true.
I also thank you for sharing good idea about the opportunity for higher studies in Singapore, France, and Portugal.
Okay.
I'm
Thank you.
thankful to Dr. Jana once again for giving basics as per my request. Since there are several students, especially bachelor students and master students are present here. I, on behalf of NIST, thankful to Santanu for making his time for us. I'm very much sure all of us enjoyed his talk and learned a lot from his talk. I'm very much thankful to him. We are also thankful to Dr. Salila Madam for giving nice introduction about our speaker. With a reminder about the tomorrow's talk by Dr. Pawan Mishra on superconductor. At same time, I, on behalf of NIST, thank you all for making your time. With this, I'm closing today's webinar. See you all tomorrow at same time. Have a nice day to all of you. Thank you, Santanu,
Thank
also
you.
again.
Thank
Thank
you,
you all.
sir.
Thank
Bye
you,
bye.
madam.
Bye bye.